Hello everybody. Today we're going to finish up section 8.1 talking about the exponential indeterminate forms. So before we get into a specific example, I'm going to talk about our general approach in every one of these problems. We're going to start with the idea of 0 to the 0. So we have a limit that essentially comes out to 0 to the 0. We're going to say that y equals that value. Well, we can use this trick where we apply a natural log to both sides. The natural log of y is equal to the natural log of 0 to the 0. According to a property that we learned back in Algebra 2, the exponent inside a natural log can be moved out in front. Now, we're going to use this approach to establish something that we can work out the value of, and then we're going to have to remember that to solve this, we're going to have to take both of these sides, e to the power of each side. So that's our general approach. For every exponential issue, this is our strategy. So we're going to start with the simplest version of this and my favorite problem of this nature. The limit as x goes to 0 of x to the x power. Well, if y equals x to the x power, then we could say that the natural log of y is equal to the natural log of x to the x power. And according to exponent rules, that is equal to x times the natural log of x. So let's say we want to find the limit of this right side. If we're going to find the limit as x goes to 0 of x ln x, now let's think we're probably going to have to talk about this from the right side due to the natural restrictions of natural log, no pun intended. But we would get 0 times negative infinity. Well, we've dealt with this before. When we have that situation, we simply rewrite it as a fraction ln x over 1 over x. Now we would get negative infinity over a negative or positive infinity depending on how we approached it. If we're approaching it from the right, it would be positive infinity, but that's not necessarily the problem here. So because we have an infinity over infinity, now we can apply L'Hopital's rule. So derivative of top, derivative of bottom. Derivative of top is 1 over x. And we've done this a lot. The derivative of 1 over x, which we can also call x to the negative 1, is negative 1 over x squared. After some simplification, we will get, remember, dividing by something the same as multiplying by the reciprocal. So I'll write that out. Dividing by negative 1 over x squared is the same as multiplying by negative x squared over 1. After simplification, we get negative x. And we simply plug in 0, negative 0, just 0. But that is not our answer. What we just determined is that the natural log of y is going to equal 0. So to solve that, we have to take e to the power of each side. E to the power of a natural log will cancel it, and we'll get y equals e to the 0, which is 1. And that's our answer there. So that's the general approach we're going to apply every single time, is to use the natural log trick. All right, now we're going to deal with something that is going to be 1 to the infinity, and we're going to do another famous example here. So we're going to do the limit as x goes to infinity of the quantity 1 plus 1 over x to the x power. Now, let's check to make sure this is 1 to the infinity. In the parentheses, 1 over infinity would be 0. 1 plus 0 is just 1. So we would get 1 to the infinity power. So if we allow y to equal the quantity 1 plus 1 over x to the x power, we can apply natural logs to both sides and get the natural log of y is equal to the natural log of 1 plus 1 over x to the x power. And we can use the trick there, x times natural log of 1 plus 1 over x. And we're going to use the same strategy as before. We're going to do the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. So let's talk about how I got that. In this part right here, I have x multiplied by the natural log. So I simply divided by the reciprocal. I divided by 1 over x. Now, why would I do that? Basically because it's much, much cleaner than dividing by the reciprocal of natural log of 1 plus 1 over x. So if we plug in infinity here, we'll get the natural log of 1 on top. The natural log of 1 is 0. And we'll get 1 over infinity, which is 0 on bottom. So we're going to apply L'Hopital's rule. We get the limit as x goes to infinity. Now, this top one's a little bit problematic. We have to apply a chain rule here. The derivative of a natural log is 1 over what was inside times the derivative of what was inside. So inside we had 1, which will 0 out, and we had 1 over x, which we've talked about that a bunch at this point, is negative 1 over x squared. On the bottom, we just have to take derivative of 1 over x, which is negative 1 over x squared. And we can cancel those. Limit as x goes to infinity of 1 over 1 plus 1 over x. So when we plug infinity in there, 1 over infinity goes to 0, so this all comes out to be 1. Now remember, that's not my answer. That means that the natural log of y is equal to 1. Apply e to both sides, and we get y equals e to the first power, or just e. Now the reason why this is a famous example is this is actually the definition of e. Back in Algebra 2, you might have gone over it. The idea is that the pattern of 1 plus 1 over x to the x power is e. Let's do it real quick with a couple of numbers just to demonstrate it. I'm going to clear some of this out. If we plug some numbers in, starting at 1, and I'm talking about plugging them into this, we would get 1 plus 1 over 1, which is 2 to the first power, which is 2. If we plug 2 in, we get 1 plus 1 half squared, which is 2.25. If we plug 3 in, we get 1 plus 1 third, which is 4 over 3, to the third power would be 2.37. If we do 4, we get 2.44. If we do 5, we get 2.488. And this is going to keep going. Let's just put in 10 to see where we're at. By the time we get to 10, we're at 2.59. By the time we get to 100, we're at 2.7048. And if you remember, the approximation that's given for E in your textbook is 2.71828. So as these numbers get bigger, this gets closer and closer to the number E that we are familiar with. So this was the original formula for E with the limit as x goes to infinity. And we just showed using L'Hopital's rule that this does in fact equal E. All right, on to the last example. Indeterminate form infinity to the 0. So here we're going to do pretty straightforward one. The limit as x goes to infinity of x to the 1 over x. So if we plug infinity into the bottom, we get infinity. Into the exponent, we get 0. So we're going to use our trick. Y equals the natural log of y equals natural log of x to the 1 over x. So when we move this 1 over x in front, it easily makes a fraction. So we're going to do the limit as x goes to infinity of ln x over x. We would get infinity over infinity here, so we can apply L'Hopital's rule. We are going to get the limit as x goes to infinity of 1 over x over 1, which simply when you plug infinity would be 0. 1 over infinity is 0. Now that doesn't mean our answer is 0, because we still have that process, natural log of y equals 0. That means e to both sides, y equals e to the 0, which is 1. Alright guys, hopefully this is a shorter video for today. This finishes up sections 8.1. We'll be moving on to 8.2 after the question day. Question day will be tomorrow.